Okay, so I know we just finished chapter 7, and now we're skipping ahead to chapter 11, and that may seem a little bit weird, but the information that's covered in chapter 11 is very helpful to college algebra. The fact that 11 starts off with roots and radicals is very nice because it's probably been a hot second since you've done any roots and radicals. And honestly, I know in college algebra, we do a pretty decent section on like solving radical equations and things like that. And all of this stuff is just expected to be known for college algebra students. And so having this to segue into college algebra is a nice transition. So a radical expression is going to look like this, where you have the radical bar. That's this, it almost looks like a division bar, but it has a little index out here typically. You have the radicand underneath, and then that's your radical symbol. These are the opposite, really, of taking like something to the second power, if it has a little 2 out there. Or this little 3 means it's the opposite of taking something to the third power or the fourth power. Math is very dichotomous in that, like, if there's multiplication, then there's division. If there's addition, then there's subtraction. If you can square something, then you can square root it. And so they go hand in hand. They're just the opposite of each other. So square roots is honestly going to be what you do the majority of because we just deal more with square roots. You will see some what we call cube roots, and we'll see that in just a little bit. That's actually what our general example up here is, where there's a little 3 out here that's known as a cube root, because if you raise something to the third power, you're cubing it. So if you have a radical with the 3 outside like that, then it's considered a cube root. One thing to note is that in general, when we take a square root, which has a little 2 on the outside, it's not going to have that little 2. It depends on the problem, it depends on the book, and it depends on the person who writes it. Remember, in math, we like to keep things as simple as possible, and so if there is no index on your radical expression, it's understood that you're taking the square root. It's understood that there's a little 2 out there. So if you are more comfortable writing the little 2, go for it, but you also don't have to. And so I want you to know that these are the same thing. And so I really should have this set equal to b so that this part, if we square b, we square both sides, then that's what we get over here. One thing I don't love about this section is that they very much specify between a positive or principal root and a negative root. And it really depends on the textbook whether or not you deal with only your positive and principal roots or if you deal with both. I will go ahead and warn you, in this book we deal mostly with positive or principal roots. In college algebra, you will be dealing with both of your roots. And so it is something to note. And so I give a general example here of what that means. What do I even mean when I say that you have a positive and a principal root and a negative root? Well, the square root of 25, if I ask you in general, most of you are going to tell me that the square root of 25 is 5. And you're not wrong. You're very right. 5 times 5 gives me 25. This holds. This is true. And this is a positive root. There's a positive symbol there, or it's a positive number. So this would be our positive or principal root. However, if I take the square root of 25, negative 5 is also considered a root. It's the negative root, because negative 5 times negative 5 also equals a positive 25. So in reality, there are 2 roots for the square root of 25. There's the positive 5 and the negative 5. And so in college algebra, a lot of times we will list both of those, and either we will list them separate with commas, or we will list them with this plus or minus, like this. Either way is completely fine and completely accurate. In this class, and on your assignments, if you are asked to take the square root, they're only going to want the positive or the principal square root, or the principal root. They're not going to be concerned with the negative. So that's one thing I don't love, because it's not completely accurate, and I feel like they could word your questions a little better, and they could say, please provide the positive or the principal square root, instead of just asking you to take the square root. That's probably just a technicality on my part, but I don't personally love that. So just know as you are working through your problems, which I did all of the homework this morning just so I could kind of see what kind of problems you would encounter and what they would be asking. Sorry, that got a little crooked. Yeah, when they ask you to take the square root of 25 or the square root of 9 or the square root of 64, they're just going to want the positive. And when you do it on a calculator, let me show you for a second. On a calculator, if you type in the square root of 64, it only gives you the principal square root. So your calculators are already trained to kind of do that. And so that's also another reason why I think Pearson does it that way. So yes, -5 would be a root of radical 25, but on our assignments here, we were going to give the positive or principal square root. Are there any questions on that before we move on? Okay, one thing to note, you cannot take the negative outside of your radical versus the negative inside. These are not the same thing. Over here on the left, we would take the square root of 25, which is 5. Then we would apply the negative, which gives us a -5. On the right-hand side, I'm saying that there is a perfect square. There's something times something that will give me a negative number. And that's not true, because in order to get a negative number, you have to have a negative number and a positive number. So it's not something that's exactly the same. This is actually not a real number. If you remember back, we've talked about, I know in Math 20, back in Chapter 1, we talk about the different types of numbers, and the big bubble of numbers is the real numbers, and that's where we like to live. But actually outside of the real numbers is something known as the complex numbers, which includes our imaginary numbers. And that's what happens whenever you take the square root of a negative number, is you get an imaginary number. And we don't deal with imaginary numbers in Math 30. You will deal with imaginary numbers in college algebra, and we go through a whole section on how this works. But know in this class that if you are asked to take the radical of -25, it's going to be a not real. You're given that option in Pearson. And if you try to do it on a calculator, it will also give you an error, because your calculator doesn't deal with non-real numbers. So that's true for square roots. That's true for any even root. So if this was the 4th root of a negative number, it's also not real. If it's the 6th root of a negative number, it's not real. You cannot take an even root of a negative number. We will see in a little bit that you can take an odd root of a negative number, though. Any questions on this? This is kind of a big thing. Okay. So in general, I wanted you to see what the graph of square root of x looked like. In college algebra, I talk a lot about what's known as the mother functions, or the basic functions of graphs, because having an idea of what these look like in general is very helpful, because we spend a lot of time with graphing. We spend a lot of time moving our graphs around. And if we don't have to do a table every time we graph in college algebra, then it makes it a little bit more helpful. Now, in this section, you are not asked to graph these in Pearson or anything else. I just wanted you to see what these look like on a Cartesian coordinate system. And so I'm going to plug in, I know that this is square root of x, and I just said I can't take the square root of negative numbers, so I'm going to start my x values at 0. And I'm just going to, nope, that's not what I'm going to do. I'm not going to do 2 and 3. Bless you. I'm going to do 4 and 9. I could do 2 and 3, but if I take radical 2, you type that into your calculator, it fills up your whole calculator screen, and I don't want to graph with that. I know if I take radical 4, that's going to give me 2 and give me quote-unquote nice answers. So when x is 0, if I plug that in, I take the square root of 0, it's 0. Square root of 1 is 1. So right now it looks like we're going to have a line. Square root of 4, though, is 2. So 1, 2, 3, 4. And then we go up. Square root of 9 is 3. And that goes up here. And so if you look, it kind of starts to get a curve. What this really looks like is it looks like half of our parabola, like a quadratic, turned on its side. We can't get negative y's out, and we can't have negative x's. So this is literally all of our graph. I mean, it would keep going on for forever, but that's how it works. So it's good to know a general picture of that. Again, you're not expected to graph them. All right, let's look at how some of these problems are going to look for you. Let's not give away the answer. Remember, with most things that we learn in math, we will start with the easiest things first. We're not learning how to solve these radical equations. What we're learning how to do is plug and chug. It says for each function, find the indicated value. We're given f of x equals radical 3x plus 7. And then it says for f of 3. So remember that 3 in there is in place of the x. This is f of x. This says f of 3. So we're going to plug in 3 and we're going to compute and see what we get out. So instead of 3x, I'll have 3 times 3 plus 7. 3 times 3 is 9. 9 plus 7, 16. And the square root of 16, since we're going to get positive or principal roots, is 4. So plugging and chugging. Here's another one. G of t. G of t equals radical 74 minus t. And we're going to find g of negative 7. What's the square root of 81? 9. 9 times 9 is 81. Any questions or clarifications on those first two? Or how we're doing any of these? Plug in the value they give you, compute out whatever it is. All right, one more. Do h of z. H of z equals radical 2z minus 15. So we're going to find h of 2. So it'll be 2 times 2 minus 15. What's the square root of negative 11? Not a real number. That's right. And that is always an option when you are computing or doing these problems in Pearson. They will give you the option to type in the value that you get, or they'll give you an option saying the solution is not a real number. So if you're trying to take the even root of a negative, it's not going to be real, and you don't have to keep going at that point.
I have a question.
Yes.
Not taking away because it's 11 is a prime number. Can you take the square root of it?
You can take the square root of 11. You're going to get a decimal, And so then you would have to make sure and read, does it want it to be in the simplified radical form, where it's just square root of 11, or does it want a decimal representation? And based on all the homework that you have today, you won't encounter anything like that. All of yours are nice, good squares and things like that. But yes, it is a good question. If you have something underneath your radical that's not a perfect square, then you can get a decimal representation, or you are able to simplify kind of like you would a fraction until there's nothing else under there that is a square. But you won't encounter those in this section. Other questions or clarifications? So far we've dealt with square roots, and like I said, most of your problems do deal with square roots. But let's look at cube roots. That's the next most common. They're the next most user-friendly. So a cube root is where you have a little 3 as your index outside of your radical. So when you take the cube root of something, what you're asking yourself is, what do I multiply by to get to that number, to the radicand? But I have to do it 3 times. And so you can do these on your calculator. It's also not a bad idea to know a lot of your basic cubes, like 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, those kinds of things. The more that you don't have to rely on a calculator, the faster problems end up working, and the faster you start seeing patterns and things like that in more complicated problems. However, I will show you, sorry, I'm going to cover stuff up for a second, how to use a calculator to do a cube root. Some of the newer calculators may actually have a cube root option, but most don't. Most have a, sorry, I'm trying to not let there be a reflection. Most have a square root option here as the second option on your squared button. And then you might have a caret or a little box where you're allowed to put other exponents. That's what this button does. And the second option for that, you'll see says X, and then it has another radical symbol. So if I was trying to take the cube root, or the third root of 8, I would hit 3 first to indicate my index. Then I would do the X radical, or the X square root, like that. And then I would type in what I'm taking the third root of. We're not 88, just 8. And it's 2. You can do 4th roots the same way. You would just put a 4 out there as your index, 6th roots, 8th roots, whatever the problem may be. That's how you end up typing it in on most calculators. If your calculator doesn't have that option and you want me to show you at the end of class, I'm more than welcome to do that. But you are able to use a calculator to find all these cube roots. Now, we just said that that was 2, and that's because 2 times 2 times 2 is 8. You can take the odd root of a negative number, because if you have an odd number of negatives, your solution is negative. Cube roots are the easiest way to see that. If I take negative 3 times negative 3, that gives me a positive 9. But then if I multiply by negative 3 again, that gives me my negative 27. So the cube root of negative 27 is negative 3. And so I put a couple of extra notes here for you that says that cube roots only produce 1 root. You're never going to get a plus and a minus. It doesn't work that way. You will either get positive or you will get negative. If you are taking the cube root of a positive number, then your solution will be positive. If you're taking the cube root of a negative number, then your solution will be negative every time. And that's for all odd radicals. So if that was a 5th root, a 7th root, a 9th root, a 13th root, whatever, it works the same way. Are there any questions on how cube roots work before we do our plug and chug style problems with cube roots? So even if it's a cube root, we're going to do the exact same process that we did with our square root. If it gives us the function and then asks us to find the indicated value, it's a plug and chug. It's just this time, if we have a negative under the radical, it doesn't mean we can't do it. We're finding f of 6. This should be a 6 over here. So this will be the third root of 30 minus 3, third root of 27, which is 3. You can't see that. Bloop. Do another one. G of w equals the third root of 9 times w minus 1. We're going to find g of negative 7. The third root of 9 times negative 7 minus 1. Third root of negative, what is that, 63 minus 1. 63 minus 1 is a negative 64. Which is negative 4. I'm taking the odd root of a negative number, so my answer had better be negative. Negative 4 times negative 4 gives me positive 16. Positive 16 times negative 4 will give me my negative 64. We'll do one more of those. Trying to find where I have some space. S of t equals the third root of 6 minus 7t. So I'm going to plug in 1. Third root of negative 1. You can take the root of 1 no matter what. You can take the odd root of negative 1 and always get negative 1. Negative 1 times positive 1, or excuse me, negative 1 times negative 1 is positive 1. Positive 1 times negative 1 gives you a negative 1. So 1's nice. We like to see 1. And then I went ahead and also put the graph of the cube root in the handwritten notes, and I'll just kind of reference it, since you're not asked to actually do any of the graphs. But it's interesting to note some similarities and some connections that we can make about these two different graphs. This is the graph of the cube root of x. This looks a lot like the cube of x graph turned on its side. Just like the first graph that we did here of the square root of x, this looks a lot like the left half of our quadratic, which is x squared. It's because they're supposed to. X squared looks like a u that opens up. This looks like half of a u laid on its side. The cube of a graph, like y equals x to the third, that graph looks like this, where it swooshes up on the right and down on the left. This is like we flipped our graph over like this and laid it down on its side. So there's definitely a lot of connections, and it's important to kind of start seeing those connections between differing graphs, just because I know you guys are all headed into college algebra, and you will be dealing with all of these graphs in multiple different ways. So again, the way I found this out was I just typed in some triples over here for my x's. I took the cube roots of those, plotted the points, and connected them. That's all you do. Are there any questions on how we plug in values or anything like that for either our square roots or our cube roots? All right. So, just some general facts about even and odd roots. Because so far we've looked at square roots, that's an even root, and we've looked at cube roots, which is an odd root. But you could have other roots. You could have the 4th root, you could have the 5th root, you could have the 28th root. They could ask you anything. And so it's important to know what we do with these. So that n out there can be any real number. It can be positive, it can be even or odd. If it is even, then it's an even root. If it is odd, then it is an odd root. Remember, you can take the odd root of negative numbers. You cannot take the odd root, the even root of negative numbers. That's what this little note down here is. And so then I did a series of examples. This is actually just like your very first example in the homework today, where they give you, I think they'd give you a square root, but I did it with a 4th root so that you can see what happens. 4th roots, again, I do not expect you to know 4th roots in terms of, that 2 to the 4th power is 16, 3 to the 4th power would be 27 times 9, 81. They get large pretty quick. But you can use your calculator the same way that you do a cube root. You can do a 4th root or an 8th root or whatever the case may be. The example here, we have an even root, and so this has got to be a positive value under here. Here, again, we have a positive value underneath. That negative is outside, so we apply the negative after we take the radical. It's kind of like order of operations, or you can think about the fact that the radical almost acts like a set of parentheses. You got to do what's inside of the radical first, then apply what's outside. The last one is not a real number because I'm trying to take the even root of a negative number, and I cannot get a real solution with that. I'm going to slide up a little bit. We're going to determine if each root is real. If it is real, we're going to figure out the indicated value. Because this is what most of your problems are like.
I have a question.
Absolutely.
Can you have a negative root?
Can you have a negative root?
Like a negative 4.
Yeah, I know. On the outside as your index.
Yeah.
We don't typically write it like that. What we will learn later on is that you can actually write all radicals as fractional exponents. And so you would look at it more in terms of a fractional exponent and deal with the negative there. We wouldn't put the negative outside with the index. All right, we got 4 kind of mini quick problems here. We're going to take the 4th root of negative 81, or we're going to take negative the 4th root of 81, 5th root of negative 32, or negative the 5th root of negative 32. First it says we're going to determine if these are real or not, because if they're not real, we don't have to do anything with them. So, is A real? No, because I'm taking an even root of a negative number. So there's nothing to do here. It's not real. Now for B, though, that negative lives outside. So I can take the 4th root of 81 and then apply the negative. 4th root of 81 is 3, so my solution is negative 3. Is C real? The 5th root of negative 32. Huh?
Yes.
Yeah. You can have an odd root of negative numbers. You cannot have an odd root or an even root of negative numbers. So I can take the fifth root of negative 32. Should be, I think, negative 2. Negative 2 times negative 2 gives me a positive 4 times negative 2. I'll show you my fingers. Gives me a negative 8 times negative 2 gives me a positive 16 times negative 2 gives me a negative 32. So as long as you have an odd index, you can take an odd root of negative numbers. So D is real, but we have to do an additional step because it has the fifth root of negative 32. We just found that out as negative 2. But it's got that negative outside. Negative times negative gives you positive. Again, you do what's included with the radical first, then you apply whatever's outside, just like order of operations. Questions, comments, clarifications? All right, I made you a nice little table of all the information. And then we'll talk about connecting radicals with absolute values. It says if A is greater than 0, so A is positive, then if you have an even root, your answer is positive. If you have an odd root, your answer is positive. If A is less than 0, it's not a real number if it's an even root, or you get a negative real number if it's an odd root. And then we threw in if A is 0, that's not very much fun, but if A is 0, you can take the even or the odd root of it, because 0 times itself, no matter how many times you do it, still gives you 0. So not super interesting. That's a typo. I see an error in my notes coming up, so I'll point it out when I get there. Okay, if we're taking the radical of A squared, that's basically saying we're taking the absolute value of A. Absolute values tell you the distance a number or a expression is away from 0. And so if A in this case was 2, the absolute value of 2 is 2. That's what it would be if we took the square root of A squared. The same thing is true for negative 2, though, because the absolute value of negative 2 is also positive 2. And when you square a negative number, you get a positive solution, and so it all works out the same way. So if you can write whatever is underneath your radical as something squared, then you can just think about taking the absolute value of whatever that is inside there. And that's what, honestly, most of your problems have you do, or at least a chunk. 7, 8, 9, 10, and 11. So about half of your homework problems have you do the absolute value method for doing these. And so we're going to do a couple and see what I mean by that. We're going to evaluate radical A squared, and then it gives us two different A values, so we're going to do it 2 different times. We're going to do it for positive 2, and we're going to do it for negative 2, so you can see what's going on here. I'm just rewriting what was up there because I know I'm going to have to scroll up and I don't want to lose anything if I don't have to. So when A is 2, I'm going to put 2 in here as 2 squared. That's the same thing as saying absolute value of 2 is 2. And here's why. Radical 2 squared, well, 2 squared is, actually it's easier than that. When you take the square root of a square, they cancel out, and so you're left with whatever's under here is how it really works out. But this will give you 4, square root of 4. If we're only thinking about positive principal roots, gives you 2. That's what ends up happening. The same thing works when a is negative 2. That's where this part kind of gets a little loopy. When a is negative 2, what's negative 2 squared? 4. Notice, same thing. This is, again, because we had something written squared, we can say this is the absolute value of negative 2. The absolute value of negative 2 is a positive 2. These are the same thing. So a lot of times we will think about it in terms of absolute values instead. What this allows us to do is it allows us to evaluate our radicals even whenever we have a expression underneath our radical and we don't know what those variables stand for. Because without being able to go to the absolute value, if I had square root of x plus 2 under there, I don't know what that value is. I don't know what anything is. I don't know how to represent it because I don't know what my x is. And if my x makes it negative, then it causes problems. And so this just allows us a way to kind of interpret things as we move through. So one thing that I want you to see here, notice that we got the same answer out, but our a's were very different. We had a is 2 and a is negative 2. So it's important to note that the square root of a squared does not equal a every time. The square root of a squared is going to equal the absolute value of a because it didn't equal negative 2 when we did the negative 2 here. I'm going to turn off that light and see if that helps. It's the glare a little bit. Is that better or worse? Better? Okay. I feel like the eye doctor. 1 or 2? Which one's better? 1 or 2? So, square root of a squared equals absolute value of a. Just keep that in mind as we work through these. And I already see that on the next set of examples, I messed that up. So I'm just going to show you the next 3 all together, and then we'll work through the others. Use the absolute values to evaluate the expressions. So we have the absolute value of 9 squared. Excuse me, the square root of 9 squared, which is the absolute value of 9. The absolute value of 9 is 9. When the number is positive that's being squared, it's really not any different than if you actually applied the square first. Here's where my notes are wrong. My notes are wrong on C. I don't know why I have that negative there. C says the square root of negative 15.7 quantity squared. Well, that means I take the absolute value of negative 15.7. So how far away is negative 15.7 from 0? Well, it's 15.7 units. So in my scanned-in notes, there's a negative there. I guess I was just eager to keep writing the same thing over and over again. B is not very interesting because it's 0. How far away is 0 from 0? Well, it's 0 units away. So not super, super interesting.
And then there's kind of isn't the absolute value of everything always a positive?
Mm-hmm. Yep.
That's the way I always thought about it. That's one of the sure is right. So it did,
It is. That's why we call it distance, because when we think about distance, we always think about positive. So Kansas City is north of us, and Fayetteville is south of us. So theoretically, I could say Kansas City is plus 200 miles away, and Fayetteville is minus 100 miles away, but that's not how we talk about distance. Distance is always measured in a positive direction, regardless of if it's north and south, east and west, or whatever. So if I'm going to Tulsa, I have to travel 100 miles. If I'm coming from Tulsa, I'm still traveling 100 miles. And that's why absolute values will always be positive, is because it measures distance.
Yeah, I just like,
Yeah.
that's usually my way to remember.
Yep.
That answer, no matter if it's negative or it's always going to be positive.
So it's going to be positive when you've applied the absolute value. Exactly right. Other questions or clarifications before we see how some of your problems are going to work today? Okay. So these are going to say simplify, and they're going to give you a radical. And sometimes they will go ahead and have it squared for you, especially if there's an expression underneath. So this one says the square root of parenthesis x plus 8 quantity squared. So we need to keep in mind that this is in reference to the a squared, which means we're going to take the absolute value of whatever is being squared underneath the radical. If that's a number, it's a number. If it's an expression, it's an expression. So in this case, it's the x plus 8 that is being squared. So I would need to take the absolute value of x plus 8. My answer when I type in Pearson will be absolute value, x plus 8. I can't go any further. I can't drop the absolute values because I don't know what my x is, and that's going to change the value within. And so I leave the absolute values up. The only time you can really drop the absolute values on these kinds of problems is if you're taking the absolute value of a single number, because then you can actually figure out what that is. But if there's an expression like this, you won't be able to drop those absolute values for the most part. This one is radical 16x squared. So this one, I need to write it as a single thing, all of it squared. But right now I have 16 and then the x is squared. Is 16 a square? Yeah. It's what times what? 4 times 4. So 16x squared is the same thing as 4 times x, which means it's 4x squared. So this 4x is my a. So this is what goes inside my absolute values. Just what's over there. So sometimes you will have to think through, wait a second, that's not written in the right format, and I need to write it as something squared, like the entire thing. So then I'm going to look at the number and say, that's what number is that squared? How can I write that? You guys can tell me what this one will be. Square root of 25y to the 6th. This is a good chapter to start dusting off all those rules way back in chapter 5 about exponents. Who's going to be brave and tell me what the answer is? Yeah. 5y to the third. Absolute value of 5y to the third. 5 times 5 is 25. And then remember, when you take an exponent to an exponent, you multiply them. That's from chapter 5. And so 5y to the third raised to the second power, we would multiply those, which gets us back to y to the sixth. And so you're taking the absolute value of whatever your a is, and your a in this case is the 5y to the third. We're going to do one more. In my handwritten notes, there's more. But by doing one more, we hit pretty much one of every style that you will encounter in your homework. And you can go and reference my handwritten notes for the others if you want to see more. This one gets to incorporate all of our Chapter 6 material where we learned how to factor. Big hint is if you have something that looks like a polynomial or a quadratic underneath your radical, it probably factors into a perfect square. So remember, when you factor, you have parenthesis times parenthesis. You look at your first term, a squared. You're going to have a and a. You look at your c. In this case, it's positive. So that means both your signs are the same. Since it's a negative here, both will be negative. And there's only two different sets of factors for 9. There's 1 and 9. Those will not add together to give you 6. And there's 3 and 3. Those will. And so it factors into a minus 3 times a minus 3. But we can write that as a minus 3 quantity squared, and then that tells us that we have it written in that a squared format. So I'm going to take the absolute value of a minus 3. I put one additional note at the very bottom of my handwritten notes that it says, if the problem tells you to assume all positive values, then you don't have to actually consider the absolute values. I didn't encounter any of those. You're going to take the absolute values. You leave the absolute values up if you have any type of a variable at play. If you have just a number underneath, then you can fully simplify and continue on with the work. In my handwritten notes, I do one more example basically of each style that we've already encountered. So feel free to take a look at those if you would like to.